Now we're moving on to this idea of a vector space, and let's look at the definition of that. So V is called a vector space where two operations, addition and multiplication, scalar multiplication, are defined. And there's a list of 10 axioms that have to be defined to have something called a vector space. The first few axioms deal with addition, the last few deal with scalar multiplication. So let's kind of dissect this definition here. So when we're talking about this definition, notice that they're using U and V for the vectors, and they're using W for a vector also, and then they're using C, D as scalars. So let's look at those addition axioms. The first one is closure under addition, and what this says is that if we were to add these two vectors together, U plus V, then we get something that also lives in this vector space. The second axiom is about the commutative property of addition. It says if we take U plus V, we should get V plus U back. So we can add them in any order. The third property is the associative property. So now we're talking about grouping. And we can change the groups, whether we're adding V plus W first and then adding to U, or we take U plus V and then add it to W. We'll get the same thing either way. The fourth property is the additive identity property, where we have some kind of zero vector that lives in the space. So V is going to have a zero vector, so that if we take any vector and we add 0 to it, we're going to get that vector back. That's what it means to be that additive identity. It's getting back what you started with. And then 5 is the additive inverse. And what that says is that now we want to get back to that 0. If we have U, what do we have to add to it to get the 0 vector back? So in this case, it's going to be, we're using the negative U as that notation, if you will, for the additive inverse. The next 5 axioms deal with scalar multiplication. So remember, C and D are scalars in this definition. The first one is closure under multiplication. This one's important. If we take this scalar times C and we multiply it by vector U, then we've got to get something that also lives in this vector space. 7 is a distributive property. If we take scalar C times the quantity U plus V, that's the same thing as C times U plus C times V. And then there's another distributive property. If we take the sum of two scalars times a vector, that's the same thing as C times U plus D times U. Then we have an associative property. If we take C times DU, it's the same thing as grouping C and D together and then multiplying it by vector U. And then we have a scalar identity. And they're calling 1 the identity here. So if we take this scalar identity and we multiply it by our vector, we should get that vector back. Now, these are things that we've been talking about for a very long time. Commutative, associative properties, additive identities, additive inverses, and so on. A lot of things we take for granted because we're dealing with the real numbers, and the real numbers are really nice. And now we're going to really start living in this world a little bit more and diving into changing some definitions around. So if we want to prove a vector space, first off, the words vector space can be a little deceiving, if you will, because we may not actually be dealing with what we're used to thinking about in terms of vectors. So if you think back to a class where you talked about vectors, maybe it was a pre-cal class. If we talk about vectors in 2 dimensions, then we're talking about vectors that look something like this. Well, a vector space doesn't necessarily have to consist of just vectors. We could talk about matrices. And matrices aren't really vectors that we could write this way. However, the definition of a vector space means that you have met that 10 criteria. And if you've met that 10 criteria, then you're good and you can be called a vector space. So just be careful about the terminology there. Vector spaces don't have to be vectors, and we're going to see some examples where they are vectors and see some where they're not vectors or vector spaces. So let's look at some examples. Remember, when we talk about proving something, then we have to go through and we have to show it works for all 10 of these axioms. So we're going to be really tedious and meticulous when we talk about our notation here and our proofs. We're going to see a lot of proofs in this. So let's start out with an easy one. Let's say we want to look at the set of all ordered pairs of row numbers in R2. And we're using the standard operations for addition and scalar multiplication. So we're just going to use the regular old addition and scalar multiplication is what that means. When we're talking about R2, then we're talking about vectors that have two components. So let's come up with some vectors, and we're using generic vectors. So there's 3 generic vectors, U, V, W. And, oh, wait, we want to do an R2, not R3. Sorry about that. I got really excited about talking about vectors. So there's 3 vectors that live in R2. And then we need a couple of scalars. So we're going to let C and D be scalars. So let's really break down what that definition of a vector space is. The first one says that if we were to add these 2 vectors together, then we should get something that lives in the vector space. So we're asking the question, is R2 a vector space? And it's only a vector space if we satisfy all 10 of these axioms. Well, let's look what happens when we add U plus V together. So we know when we add these together, we add white components. So U1 plus V1 is our first component. U2 plus V2 is our second component. To have closure under addition, that means that whatever you come up with has to live in the space. So, does this vector live in R2? And the answer is yes. If we were to add two-dimensional vectors together, then we will get something else that is a two-dimensional vector. So the first axiom has been satisfied. We are closed under addition. The second axiom we need to check is commutative property. So if we take U plus V, we're going to get the vector U1 plus V1, U2 plus V2. Now we're talking about the properties of row numbers here and here for those components. And we know we can add row numbers in any order. And that's the same thing as V plus U. So we have satisfied the commutative property of addition. So we're good there. Now let's look at 3. We want to know, does the associative property hold? So we have U plus V plus W So let's use order of operations and add those together. And then continue adding. So when we're adding here, we're thinking about that V1 plus W1 and that V2 plus W2 kind of as a unit. So if I add that first unit there to that U1, I'm going to get this. If I add this unit, V2 plus W2 to that U2, I'll get that. So now we're talking about what are the properties of row numbers and how can I use them to tweak this. So we can use them to tweak that this way, kind of by grouping that U and V together. And then now we can undo that addition of vectors. So there's our first component. And then there's our second component, U2 plus V2 is the second component, plus vector W. And then by definition, that guy is U plus V. And then we have plus W there. So you can see how that associative property holds. And then we're going to look at 4. 4 is all about a zero vector. Do we have a vector so that if we were to add to our U, we're going to get back U? Is there something that we could put in that blank? That's how we need to think about this. And the answer is yes, there is. And we can put the zero vector in there. Because if we were to add those together, we will get that guy back. So the question is, in this step, do we have a zero vector? And the answer is yes. The zero vector is the additive identity. And we do have one. 5 is about the additive inverse. The question is, do we have a negative U that lives inside of this potential vector space? Well, we're talking about two-dimensional vectors, right? So, and under our two-dimensional vectors, we can have any row number in there. Because remember, we're in R2. And R2 is all about row numbers. So, if I have U1 here and U2 here, then the additive inverse would be negative U1, negative U2 as a vector. And if I add those together, I do get that zero vector back. So the key to this is really understanding that this guy does live in that space. So that when I add that negative U vector to the U vector, I get that zero vector back. And we didn't really talk about this with that zero vector, but let's talk about that I did up here back in 4. This guy, notice this guy lives in the space. This is also a vector in R2, and that's important because whatever your zero is has to live in the potential vector space that you're talking about. So you always got to ask, does it live there? If it lives there, then you're good. If it does not live there, then you can't use it. You can only deal with things in space. So those are all your addition, the addition part of the definition for a vector space. Now let's talk about the scalar multiplication part. First one, we need to look at C times U. Do we have closure is what we're asking. So closure under scalar multiplication means that if I were to multiply these two vectors together, then I get something that lives in R2. And that's definitely going to happen here. If we take any scalar c, and we're going to talk about c's being part of the row numbers. So unless otherwise stated, we're going to assume that scalars are going to be a row number. So if I take a row number, that's a scalar, and I multiply it by a vector, do I get another vector that's an R2? And the answer is yes. We get something that's an R2. So we do have closure. And that's under scalar multiplication. So then we need to talk about a couple of distributive properties. So if I take C and multiply it by the sum of U and V, I'm going to have C U1 plus V1, C U2 plus V2. So now we're talking about this guy being a row number, this one being a row number, and what are your rows of row numbers? Well, your rows of row numbers says that you can distribute. And that's the same thing as this. Which is the same thing as this. Which is the same thing as this. So you can see how we just proved that axiom holds. So 8's another distributive property. Now we have two scalars. When you think about this sum, C plus D, I want you to think about it like a unit. So if I were to multiply this number through, then I would have that number, C plus D, whatever it is, times U1, and then C plus D times U2. And now I'm dealing with row numbers here and here for the first and second components, so I can distribute. So I have CU1 plus DU1, and then CU2 plus DU2. So now I'm dealing with properties of row numbers. And then we can undo some some addition that happened here. And then lastly, we could factor that C out and then the D out. So we have CU plus DU. So that's what we wanted to prove. Both of these are distributive properties. None is about the associative property for scalars. So let's go through and verify it. U is U1, U2. So we have DU1, DU2. So we could change our grouping here because now we're inside and we're looking at each component separately when it can apply those rules of row numbers. There's rules that we tend to take for granted. Now we're treating that CD as a unit. There's our associative property. And then I'm going to put 10 over here. This is our scalar identity. And our identity here is 1. This 1 is really just a placeholder, by the way. In most worlds, 1's going to work, but not every world, which we'll see shortly. So I'm putting a check after each one to let us know that we have verified that that works. This is a scalar identity property. So now we've gone through all 10 axioms and we have proven that every axiom holds for R2. So we're going to say, yes, this guy's definitely a vector space because all 10 axioms hold. Now you can see this process can be a little tedious, going through and verifying everything, but it's kind of like a necessary evil to determine whether or not we definitely have a vector space. So let's look at another one. Suppose we were looking at the set of all ordered n-tuples in Rn. So the difference between this one and the last one is that we were in 2 dimensions in the last one. Now we're in multiple dimensions. And we're still looking at the standard operations for addition and scalar multiplication. Do you think this guy is going to be a vector space? Take a minute, pause the video, think about whether or not you're going to have a vector space there. So the answer is yes, we're definitely going to have a vector space. So if we wanted to go through and prove it, and I'm not going to prove all of this one, but you can use vectors u1, u2, all the way up to un for u, v, and w. This one's going to be very similar to the last one in the way that it's proven, because we're still dealing with standard definitions for addition and scalar multiplication. It's just now our vectors are a little bit bigger. But in both cases, we're still in that vector world.